Alright, this is thermodynamics 2, homework number 2, which is Clapeyron problems and equilibrium and Gibbs free energy. And as you can see on there, this is going to be a Clapeyron problem. Okay, so this one actually builds upon the previous problem. Refer to the other video if you want to know more about the Gibbs free energy. But basically what's going on in this problem is we have solid iron going from the ferrite phase to the austenite phase at 1185 K. Okay. So it says for number 2, and those are the details for number 2. Let's say we have another metal that behaves the same but at 900 K. So I guess this one's at 900 K. Okay, so we have some mystery metal that does this at 900 K. The density of the ferrite phase, so we have a density of the ferrite phase is equal to 0.15 moles per cc. And then the density of the austenite phase is equal to 0.10 moles per cc. Okay. If the phase change occurs at 800, but at 0.01 bar, what is the enthalpy of the phase change? Or rather, like, what's the delta H associated with this phase change? Okay. Well, so first, what's the first thing I do with these problems? I recognize it as a Clapeyron problem. How do I know it's a Clapeyron problem? It talks about phase changes. And anytime I'm curious about phase changes and the temperature of phase change or the pressure of a phase change or the enthalpy of a phase change, my brain should automatically go to Clapeyron problem. Okay, and as soon as I recognize it as a Clapeyron problem, I write in the Clapeyron equation. Okay, which I have done up there. Okay, what's the next thing I do? See, I hear crickets in the background. I write down my assumptions. Okay, so what are my assumptions that I can have? Okay, first off, am I can be an ideal gas. Okay, so that's an assumption I can have. Is the austenite phase an ideal gas? Nope. What about the ferrite phase? Nope. Last time I checked, solid metal was not an ideal gas. So that one's a no-no. Okay. Let's see here. Another one. Okay. My volume of phase alpha is much, much bigger than volume of beta. Okay, and volumes are like density, so this could be written as density of alpha is much, much less than density of beta. Okay, so is 0.10 much, much less than 0.15? No, they're pretty dang close. So that's another one that's a big fat no. Okay. All right. Another assumption that we like to make is that delta H is constant with delta T and delta P. That the change in pressure and the change in temperature relative to our reference point is small. Okay. Well, that's what we're looking for in terms of that. So we have to ask ourselves, is the change in pressure, is the change in temperature small? Well, the change in pressure is 1 bar, essentially. Okay, that's pretty small, especially when it comes to a metal. Okay, the change in temperature is 100 K. That's kind of getting on those borders, but the problem is it doesn't say anything about, you gotta look at the problem now at this point. Okay. It's asking, what is the enthalpy of the phase change? I kind of have to assume it is constant. I can't solve for an equation of delta H. Okay. Now, if I'm actually an engineer or whatever, what you need to do is you need to make the assumption and then verify that assumption. Go check the measurements, and does that seem accurate? Okay. So But let's just assume that it is constant. So we'll call that assumption number 1. Okay. And then the last assumption that we can make is that delta V is, constant with temperature and pressure. Okay. So when can I not assume that? Well, there's a couple ways. A, if I have a gas. If I have a gas, it is not constant with temperature and pressure. I mean, it is fluctuating. Okay. Do I have a gas? Nope. Okay, but I also have to ask, is the temperature change big and is the pressure change big? But we've already established with enthalpy that it's going to be acceptable. Okay. And so it's going to be acceptable with the volume too. Okay, so those are our 2 assumptions, and these are our not-so assumptions. Okay. Now that we've established our assumptions, well, now we apply them to the problem, and, mathematically, separate and integrate, and do some math. Okay, so first we separate and integrate, separate, and then have an integral symbol. So dp equals delta H over T delta V dt. Okay. From P1 to P2, T1 to T2. Okay. And now let's apply our assumptions. Okay. We haven't assumed anything at this point. Okay. So let's apply our assumptions. So the first one says delta H is constant. So mathematically, what does delta H is constant let me do? It lets me pull it out of the integral. Okay. And in terms of the work I want shown, is I want you to have a little arrow or something, and then maybe a little, 1. Just so I know that you're not just pulling out of the integral because you see me pull it out of the integral, on 20 other problems. Pull it out of the integral because of assumption 1. Okay? Let's look at assumption number 2. It says delta V is constant with delta T delta P. So what does that allow me to do? Same thing. It allows me to pull it out, and I would do the same thing. I put a little 2 there to indicate that's why I'm pulling it out, because I've assumed that it's constant. Okay. And then, okay, I'm left with, from P1 to P2, dP is equal to delta H over delta V dt over T. Okay? So I'm going to kind of erase some of this. I'm going to erase all this assumption. So, we've applied our assumptions. We don't really know what they are anymore. So we can, erase those really quick. Okay? All right. So, well, what's the integral of dP? P. Okay. Delta H over delta V. Okay, what's the integral of dt over T? From T1 to T2. Natural log of T. From T1 to T2. Okay. Now, I can simplify this, but we go over the problem. It says the density, okay, blah, blah, blah. What is the enthalpy of the phase change? Okay, so I know P2 and P1. They are 1 bar and 0.01 bar. Okay. So our P2 is equal to 0.01, and our P1 is equal to 1. And our T2 is equal to 800, and our T1 is equal to 900. Okay. And then our delta V, are we given V? No, we're given density. So delta V is equal to, V alpha minus V beta. Okay. This is not delta rho. It's not delta 1 over rho. Oh, sorry, 1 over delta. Yeah, so this is not delta rho. It is also not 1 over delta rho. It is equal to delta 1 over rho. Because V alpha is 1 over rho alpha. Okay. And so how they should be written in terms of rows, if you're going to use proper math and not naughty math, is it should be 1 over rho alpha minus 1 over rho beta, which is not 1 over, which is not 1 over rho alpha minus 1, minus rho over, rho beta. Okay, it is not that. Not it, okay? So, but, we can plug those things in. So, and we always plug in the math before we plug in numbers, right? So let's rearrange this a little bit more. So we'll erase our knowns. We'll plug those numbers. Well, you'll plug in those numbers. I'm not going to plug in those numbers. I'm too lazy, okay? So this becomes P2 minus P1. And I'm solving for delta H. So, okay, so that's times delta 1 over, so I've got 1 over rho, well, I'm multiplying it, so that's, no, it's, remember, this is delta 1 over rho, so 1 over rho alpha minus 1 over rho beta, okay? So there's my delta V, and then all divided by natural log of T2 over T1. It's because the natural log rules. And that's my delta H that I'm trying to find. Now you might be like, okay, well, which is alpha and which is beta? Well, that will, essentially, that will work itself out so that this is the right sign. Okay, so if it takes enthalpy to make the phase change, which in this case we know it does, this should be positive. Otherwise it should be, if I'm going from something that is high enthalpy to low enthalpy, like, condensation, then this should be negative. Okay, but, well, that's actually all that is. I plug in my numbers and I should get delta H from there. Okay? So it's just plug and chug at this point. But this is your quote-unquote final answer that you would have on a quiz or something.